Yeah, welcome to pattern analysis. We will talk today about the training of hidden Markov models and another type of graphical model, the Markov random fields. As usual, I brought a couple of questions. Talking a bit about the training, clarifying the role of the alpha and beta caches in the training, and then a little bit about Markov random fields. So the questions, they are relatively straightforward, but as usual, of course, we can also take this opportunity to talk about other things as you deem it like interesting or necessary. Yeah? And if we look a little bit at the weeks to come, so this is like week 10 now. Next week we will have another topic about Markov random fields, and this is a particular inference method that uses graph cuts and is able to provide globally optimal solutions for binary labels. And then in the 12th week, I will come back to this promise originally made that it might be interesting to have a look at the paper that proposed the variational autoencoders, because it actually uses a lot of the techniques that we learned about in class throughout the semester. So I think it's a nice bracket around a couple of concepts that we learned about. Yeah, and then we're essentially done. Of course, we can meet still, but this would close the lecture then, and we can prepare for the exam. Okay, about the hidden Markov model training and the Markov random fields. Is there something that you want to discuss or want me to explain or clarify before we start in the questions, like right away? If not, then we can have a look at the questions. So okay, so I would like to discuss a little bit the hidden Markov model training. So a direct maximum likelihood estimation is not feasible to get the hidden Markov model parameters. So as a general question, like how is it done instead? Like what is the approach to mitigate possible problems that might occur in this direct maximum likelihood estimation? This is a more general question, and then there's a relatively specific question, like we learned about the alpha in the forward algorithm and the beta then in the backward algorithm. So how do they come into play in the training? Okay. So first things first. The training procedure itself, how does it work? Sorry, you're saying, so it's not a direct maximum likelihood estimation. Okay, so what would be a direct maximum likelihood estimation? A direct maximum likelihood estimation would be something like a procedure that that comes up with values for A, B, and pi, like that directly translates, that directly translates training sequences into parameters A, B, pi. For example, by saying, okay, like if I don't know, we could do like a statistical analysis, no, and could say, okay, if the letter S comes up in 30% of the cases, we put in like a 30% here for these output states or something like this, no? But this is not how it's done. So, because it wouldn't work very well. How is it done? Like in general, what is the approach to the hidden Markov model training? Yeah. It's right. These Baum-Welch formulae. No? This is an expectation maximization algorithm. So there's this instead of the direct estimation, you always have this. You have this two-step type of optimization that you say, okay, let's get an estimate on the hidden variables, and then let's update the parameters for the observations. No? So it's this indirection, and we expressed it with this. The posterior of the hidden variables, is it y or is it z? I don't know, doesn't matter. Posterior of the hidden variables given the observations and the previous parameters times, and now the full data likelihood x and y given the new parameters. No? So this is what is maximized. No? And this is an expectation maximization procedure. This is the exact same equation that we have in the generalized expectation maximization in in the variational inference section. No? So if you compare this, it's the same tool. No? And this indirection, it helps to sort of, let's say, to pre-segment these input sequences such that we can better map this to the data. Could be one way to look at it, no? For example. Okay. Does it make sense? So what could be 2 or 3 sentences describing this training? Like to come up with a solution here. Come on, in 4 weeks I want you to write these 2-3 sentences. Don't be so consumer facing. This is terrible. Yeah. Mm-hmm. This is sentence number 1. We use an expectation maximization algorithm. Yes? Mm-hmm. Okay. Yeah. Yeah. And right. So this posterior of the hidden variables you use for updating the parameters. This would be your 3 sentences, and everyone would be happy. No? Yeah. Okay. Good. Thank you. Since you mentioned the alpha and the beta already, so what is the specific role of alpha and beta? How does it come into play, and what does it, what type of information is contained in the alpha and in the beta? What is Dorte? Yeah. So alpha, let's form a proper sentence. So alpha T, transitions were like Aij, no? But the alpha, sorry, here we need a state I. So if we have alpha for state I at time t, what type of information would this be? No. You're talking about transition probabilities. So this is a probability to go from state I to state j, and the sum, like overall, like all outgoing probabilities over all ij, this is this is 1. No, but the alpha, this is the intermediate variable in the forward algorithm. So if you say this is my time, like going from 1, 2, 3, and so on until time t, yeah, it's the sum of the probabilities of all paths. Let's say we have a 4-state HMM, yeah, and we look at this HMM until time 3 is fine, yeah. So let's say t equals 3. This t, yeah. So this is state 1, state 2, state 3, state 4. What possibilities do we have? We start in state 1, we stay in state 1, we stay in state 1. This would mean, okay, this is one possibility to be in at time 3 in state 1. So let's have a look for in particular at the probability of being at time 3 in state number 1. So this is one possibility, yeah. How likely this is, we can calculate it by taking these transition probabilities, the output probabilities, and so on. What other possibilities are there? Well, we could start in state 1, could go to state 2, could go to state 1. Or we could start in 1, go to 3, go to 1. Or we could start in 1, go to 4, go to 1. Or we could start in state 2, go to 1, stay in 1. Yeah? So if we enumerate all these possibilities, then the sum of all these possible paths, we might also have started in state number 3, went to 1, stayed in 1, or started in 3, go to 2, go to 1, and so on, and so on. So the sum of all these possible paths that end at time 3 in state number 1, this is what alpha is. Yeah? Okay. And beta, symmetrically, it comes from the future. No? Yeah. So if the sequence in total has a length of 5, let's say, yeah, then beta is the sum of all, beta sums all paths that, So we could end in state 1, could before that be in state 2, and before that be in state 1, could end in 3, be in state 1, could be in 4, be in state 1. So could end in state 2, before that be in state 1, be in state 1, and so on and so on. So the sum of all possible paths that at time 3 are in state 1 and that will from there span to the final state. Yeah? This is what beta stores. This is important to understand because this is what, these are many, here we are. Because we can, like with this dynamic programming approach, we can relatively efficiently calculate the alpha for all states for a specific time step. Yeah? Also the beta for all states for a specific time step by following these iterations. And yeah, so it plays an important role in the training. What role does it play when we're talking now about the expectation maximization algorithm? What is it good for? For the? It's an average, yeah. It's like you can say it's like a marginalization of everything that has happened before. Yeah. So all these state transitions that you had at a time earlier than 3, you marginalize over them, and you're taking them out from the consideration, and beta marginalizes over everything that happens afterwards. And this gives you a little bit of freedom to look at what actually happens when we're processing the third symbol in the chain. No? So for that third symbol, you can then calculate a relative frequency for the state transitions. You can calculate, okay, like to which state should we attribute this observation that we have for the third symbol, no? Because now we can calculate a relative frequency. Oh, how likely is it that we are in state number 1 for the third symbol? How likely is it that we are in state number 2 for the third symbol, and so on and so on. No? And having that allows to map these observations properly to individual states according to the expectation, like in which state might we be at this point. No? If we restrict it to time 1, we can assign the starting probabilities, and if we do not converge this here at one state, but if we leave one state transition space, such that we say the alpha goes until time 3 and the beta only goes until time 4, then we can single out these transitions between time 3 and times 4. So this is the key, really, to learn properly what these parameters are. No? So, and this is all enabled by getting a grip on these hidden variables, like where might we be at time t. No? That's important. So have a look at this. I think it's an important mechanism to study. And it's very instructive, so you can definitely learn something here. Okay. Shall we talk about Markov random fields, or shall we talk a little bit more about hidden Markov models? Both is fine by me. Just have to tell me which direction we want to go. Markov random fields. Okay. The posterior of the Markov random field. Why is it intractable to calculate the posterior distribution of a Markov random field, and what can be calculated instead? Then let's briefly talk about the independence assumptions in a Markov random field. Like just list them, and then an advantage about distributions with, an advantage of potentials over distributions. Okay. Markov random field. First of all, what is a Markov random field? U2 passive, if I may say this. No, I don't know. I mean, we need to meet, no? Like we all can make better use of this time, no? I don't know, read a book in this. Write you down the solutions. You can double check the ChatGPT. We all meet for the exam. You're happy, I'm happy. I don't know. Today is a disaster. Only double checking. This is like there's like no cognitive effort here. This is literally all stuff that is discussed on the slides. No? Why is it intractable to calculate the posterior distribution? Because these are exponentially many terms. Yeah? Number labels raised to the power of number of variables. This is literally in the video. Not sure. Shall we have a conversation about the mode of the lecture? Do you prefer like a passive consumption type of lecture? We can do this. It's not a problem. I mean, we don't have to meet here. It's my time and your time that we spend here by sitting here. I don't know. Or do you prefer me to just present things like in a TV type of fashion? We can also do that. Maybe we should have a conversation about this. Because of course I don't need to ask these questions. No? It takes me 10 minutes to write down the solutions to these 5 questions and we're done. It's fine. No? It's a very quick process. Everyone can go back to his business or her business. No? I don't know. You want to say something? No, there's no way. Okay, so if these are the observations, these are the associated hidden variables. And if you go for discrete labels, then it needs to be more than one label, because one label would be trivial. So let's say the minimum number of labels would be 2. Then like the possible labelings here would be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. No? It would be 16 different labelings, because 16 is 2 raised to the power of 4, the number of different labels raised to the power of the different variables. So, and this is a general problem, a general limitation in these Bayesian methods, that if we're calculating something like posterior equals likelihood times prior divided by evidence, then the evidence means it's a summation over all possible labelings. No? So this is always an exponential term, unless you have a situation where this for some reason collapses or so. No, but if we say we have number of labels raised to the power of variables. So this means if the number of variables is what is increased, then the order of growth of this expression is exponential in the number of variables. Yeah? So the order of growth and this is in the number of variables. Yeah? And this is at many occasions so. No? And in the Markov random fields, we are seeing this again. No? So we again have this problem that we cannot evaluate the evidence, and this means we cannot normalize the posterior distribution, or in other words, we just don't get the posterior distribution within a reasonable amount of time. Yeah? So the best thing that one can do is to say, well, okay, I'm not getting this distribution because I can't normalize it, but I still can go for the maximum. No? And this is the maximum likelihood solution. No? So like whatever values I get, I can figure out the maximum. And this is what you can do when you do inference with a Markov random field. No? So you can do a maximum likelihood estimation. Okay. The Gibbs sampling and also the graph cuts next week, they will not make an attempt to give the actual posterior distribution, but only the solution, the most likely solution, let's say. No? And with the Gibbs sampler, we have the additional problem that it's not globally optimal. So it will probably not even be the maximum likelihood solution, no? but an inferior solution to that because of local optimality. So the evidence is one stumbling block. Okay. And there's no way to get around this exponential term. No? But there's also if we say we need only the likelihood, we only look at the likelihood and the prior because evidence is hopeless. Also, the likelihood and the prior require something such that we can process it. Yeah? And this is where the independence assumptions come in. So the independence assumptions make the likelihood and the prior tractable. Yeah? So So what independence assumption do we need for the Markov random field? It's the same as for the hidden Markov models, essentially. No? We require that one observation depends only on a single hidden variable. And the second aspect is that a hidden variable only depends on a neighborhood of hidden variables. It's an undirected graphical model. So there's no notion of a predecessor or successor or anything, but there's a notion of a neighborhood. So this means if we have an observation has a single link to a hidden variable, and the hidden variable can have various links to neighbors, but all these are only pairwise links. Yeah? So the pairwise links, we wouldn't necessarily need them to be pairwise for the Gibbs sampler, but we will necessarily need them for the graph cuts next week. Yeah? For the Gibbs sampler, we could also say, let's form a group of 3 variables, for example. Yeah? Depending on what neighborhood structure we define here, we have to define different energy functions. No? Because these, with the transition to a Gibbs random field, instead of specifying this as a joint distribution, you can also specify this as a potential that consists of e raised to the power of minus an energy function involving this variable. And depending on what clique size you define, you need to define a function of different cardinality here in the exponent. Yeah? Okay. In practice, people only define functions between 2 hidden variables or between an observation and a hidden variable. Okay. What is the advantage of a potential? The advantage of a potential is that you can essentially define a function in your problem space. No? With this, in a potential, you can embed an energy function. This energy function can be a function where you have a minimum that is derived from the problem description, like for the example of the denoising, that you say, okay, I have two types of energy functions. One energy function requires that the solution is close to the input image, and the other energy function requires that 2 neighboring pixels are similar. No? And this, in the result, gives then a denoised image. Yeah.
Basically, with potential, we define a function for
Yeah, hold on. If we take the example of the denoising, in a Markov random field, we have two types of distributions that we would need to specify. One distribution would be the data term, which is the probability that, or would be the likelihood then in the Bayesian, no? The likelihood that we're seeing pixel xi, that intensity, given that the hidden label is this and that. Yeah? And the other distribution that needs to be specified is a joint distribution between yi and yj. So so you could say, okay, this distribution is not so hard actually. And if you like a Gaussian, for example, you can take a Gaussian, indeed. So you can say this shall be a Gaussian, a Gaussian. So xi shall be evaluated in a Gaussian function with mean yi, and I don't know, say a covariance, some covariance, or standard deviation, even if it's 1D data, some standard deviation or variance, and we can evaluate it. You can just plug in 1 divided by and so on and so on. Okay. So this is fairly easy, but it's more complicated to get this pairwise term right, because yeah, maybe you could define it as some form of a difference or so, but that's a weird. So then it wouldn't be a distribution of yi and yj. Okay, you could say that you have something. Let's try to make this like as a table of values, and you could say, okay, on the diagonal. So if yi has essentially the same value like yj, you assign here a large probability, and on the off diagonals you have, or let's just call it a low probability here. Yeah. And that way kind of mimic what the potentials are actually doing, no? So that way you can sort of like backwards say, okay, if I in a Gibbs random field, if my energy function is just the difference between xi and yi, maybe squared, maybe not, I don't know, depends. And here I put in the difference between yi and yj, then I can kind of mimic it by defining these two distributions like that. This is a possibility, but it's still kind of unclear. Then you have to see like, okay, like what do I choose? How do I choose this variance? How wide do I choose this diagonal or so? No? So it's still, and it's a bit messy. No? So whereas here with these energy functions, they are relatively easy to deal with. No? At the end of the day, what people are usually using is that they have like one weighting term between them, something like, so they say, okay, we have an energy term for yi and yj. This is weight with a lambda, and then we have an energy term for yi and xi. And this overall pairs somehow of I and j. So it's relatively easy. You have one weighting parameter between the two, and you're done. Right. So it's not so it's not so that it's impossible to define a Markov random field directly in terms of these distributions, but it's less convenient, let's say. No? So yeah. So the transition, I think, in physics, they are defining these probability distributions directly because it's the most natural representation for their physical models. But other than that, usually this transition to the energy functions is done, and then the problem is specified in terms of an energy minimization problem, which maximizes these potentials and gives them the most likely solution. Yeah? Okay. So I think, yeah. So to summarize, for many tasks, these energy functions in the potentials are relatively easy to define, and then we only need one balancing parameter between the unary potentials and the pairwise potentials, and it's done. No? And then you can give it to an optimizer like the Gibbs random field or next week to the graph cuts, and it just calculates the solution. No? Okay.